In this lecture, we want to talk about dynamic finite element modeling and focus on mode superposition, or sometimes this is called modal analysis. So as we have in the past a couple lectures, let's just begin by recalling the discretized equations of motion. And those equations, remember, was the mass matrix M times U double dot. And I should just remind you that U double dot could be a function of time, right? Plus K times U, also a function of time, is equal to some reaction vector R, also a function of time. Okay, that's equation 1. So we've previously shown how to implement via the Newmark beta method the implicit integration of these equations. So if we care about the exact solution, we want to just step in time to solve it, we know how to do that. Okay, but also in a lot of times a good approximation for many dynamic problems can be obtained just by considering a small subset of all the modes. So what do I mean by that? Let's suppose you're modeling a wind turbine blade or something like that, for example, and it's rotating maybe at a rate of 20 RPM or something like that, or maybe 3 RPM, right? Probably 3 RPM. Right, so something relatively slow. You don't really care about the wave propagation down the blade that might be occurring, you know, at a velocity of hundreds of meters per second, or maybe even more than that. What you care about is the low frequency modes, kind of the large dynamic effects on the blade. So you probably would like to find a way to take equation 1 and just solve it for the things you care about, as opposed to having to solve the exact equation. Okay, so let me try to write that down. So, you know, in addition to the wind turbine example, another example might be modeling an earthquake, right? You want to see how an earthquake is going to affect a building. And the nature of the frequency that the earthquake is, let's say, vibrating at versus all the possible frequencies that are in that building mean that maybe there's 1,000 or more modes, right, in your building, but you probably only care about maybe the first 20 modes. So what kind of a method could we develop to exploit that we only care about sort of a subset of the entire dynamic response? Okay, so sorry, I just wrote that example down for you. If we could find a way to do this and only look at those first, let's say, 20 modes in this 1,000+ mode problem, this is going to result in a significant computational time savings. And the savings is going to be both for the eigenvalue, eigenvector extraction. We don't need to extract them all, just up to a certain frequency, but also on the integration in time of these modes. So the question that I'm going to pose sort of at the end of this just intro is, how could we transform equation 1 from an equation that's written on displacements to an equation that's written in terms of a summation of all of our possible vibration modes? Okay, so that's the question we're trying to answer. Okay, so how are we going to do this? Well, we're going to begin by returning to the eigenvalue problem that we developed when we first talked about natural frequencies and mode shapes. So let me remind you again. Let's just recall the eigenproblem that arose from the calculation of natural frequencies for some n degree of freedom system. Okay, and that set of equations, if you remember from that lecture, looked like K, the stiffness matrix, minus omega squared times m. That quantity times the vector U bar, which we said was an eigenvector, is equal to 0, right? Let's call that equation 2. So I could also rewrite this and say, or if I wanted to, I could write this as K times U bar is equal to omega squared times m times U bar. Okay, let's call that equation 3. So if we were to solve this, I'm not going to talk about how to solve the eigenvalue problem. That's a topic for a different course. But if we solve this, what are we going to get? For an n degree of freedom system, we should end up with n eigensolutions. And those solutions will be eigenvalue eigenvector pairs. So we would have omega 1 squared as our eigenvalue, and we'll call it u bar 1 as the corresponding eigenvector. And then the next, let's say we have omega 2 squared and a corresponding eigenvector u bar 2, right? And dot, dot, dot up to n of these, right? So it would be omega n squared and then u bar n. Okay? So a couple things to note here is that we're going to normalize our eigenvectors, which hopefully you remember doing previously. But previously, when you've ever normalized eigenvectors, you probably just set the magnitude equal to 1, okay? So we're going to normalize the eigenvectors with respect to the mass matrix. So the solution of equation 2 yields these n eigensolutions, as I've shown here, right? Where the eigenvectors are orthonormalized with respect to the mass matrix, such that we could write u bar j transpose times the mass matrix times u bar I, right? That quantity is going to be equal to 1 only for the case where I is equal to j, and it's going to be equal to 0 for I not equal to j. Okay, let's call that collectively equation 4. Okay, so that's just the definition. So we're going to normalize all of our eigenvectors in such a way that equation 4 holds true for all of them. Okay, so what that lets us do then is now we can go ahead and we'll pre-multiply by u bar transpose, right, for any given ui. Okay, so and we'll do this on equation 3. Okay, so thus pre-multiplying equation 3 by the quantity u bar I transpose gives the following. It says u bar I transpose times the quantity k times u bar I in this case, okay, is equal to omega I squared times u bar I transpose times m times u bar I. Okay, well, I just defined what u transpose times m times u is, right? That's 1, right? So this is going to be equal to omega I squared. Let's call that equation 5. So based on this result, we can define what's called a modal matrix. And we'll define that modal matrix as the matrix FEA, capital Phi, where the columns of that matrix are all the eigenvectors that are normalized with respect to the mass. Okay, so if we were to write this out, we'd write that this Phi matrix is equal to all of our eigenvectors, rather, so u1 bar, right, that's been normalized to satisfy equation 4. And then the second column would be u2 bar, right, and we would go up, dot, 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 up to the nth column, which would be un bar. Okay? Let's call that equation 6. So associated with this, we can also define what's called a spectral matrix. And we'll call that matrix omega squared. And it's going to be given as follows. We'll say that omega squared is going to be equal to the following. It's going to be a diagonal matrix that looks like omega 1 squared, omega 2 squared, dot, 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 all the way down to omega n squared. and then these are just zeros because it's diagonal. So make sure you remember this. This is diagonal. Call this equation 7. And so now let's look at equation 4. Well, that equation 4 is really written in a pretty simple way that looks like we get this value of 1 only when ui and uj are equal. Well, it lets us, we can take equation 4, combine it with equation 6, and we can write the following. We can say that phi transpose times m times phi, right? Where remember phi is just columns of the eigenvectors. So if a single eigenvector yielded 1, right? So I can't show you equation 4 because it's out of the screen now. Then you probably expect this quantity to be 1 on the diagonals, and you'd be right. And this just becomes the identity matrix. Let's call that equation 8. So we can then write something similar using equation 5 and also equation 6 and 7. Okay, so combining equation 5, 6, and 7, we can write that we have, let's take this now, matrix phi transpose times k times the matrix phi, right? So if in the single eigenvector case it gave us just omega, you can imagine now this is going to give us the spectral matrix, right? So this becomes omega squared. And let's call this equation 9. Okay, now we need to exploit a property of the eigenvectors, and that is that in this particular case they span the space, okay? What does that mean? That means that we could write any displacement as a linear combination of all of our eigenvectors. Okay, so that means I can take and say that u, right? And it could be a function of t, right? It's going to be equal to a linear combination of my eigenvectors is going to be u1 bar times some coefficient. We'll call it z1, which could be a function of t, plus u2 bar times z2t plus ... up to n, right? un bar times zn is a function of t, right? Let's go ahead and call that equation 10. Okay, or, so I could write this, right? Here you can start seeing what I'm going to do here. I have a column vector of this is a column vector of all of my eigen vectors, right? So I could write this as u of t is equal to this big matrix phi, which is my matrix of eigenvectors, times the quantity z of t, right? Where z represents all of my coefficients. Call that equation 11. Okay, and I could similarly do something for the acceleration, right? So similarly, we could write that u double dot t is equal to phi times z double dot of t. All right, let's call that equation 12. So what is this z term? Well, we already can see it in equation 10. The z values are basically the weights of each eigenvector or mode shape. And they're referred to as modal coordinates. Okay, they also can be called modal displacements, or sometimes people will call them generalized displacements. Okay, so that's where the z value is. But in equation 11, what is that matrix phi doing? Well, in equation 11, that matrix phi is acting as a transformation from the modal coordinates to displacement coordinates, right? So now what we have is a mapping between the modal and the modal side and the displacement side. So now we can go ahead back to our original equation and transform it. Okay, so substituting equations 11 and 12 into equation 1, we transform our discretized equation into an equation on modal coordinates. So what does that look like? That looks like m, and then now that u term, well, we already said u was phi, u double dot rather, is phi times z double dot, which is a function of t also, right? Plus k times u, and u is phi times z, which is a function of t, right? Equals r of t. Let's call that equation 13. I'm now going to pre-multiply by phi transpose because I now have some identities I can apply here. And I end up with phi transpose times m times phi times z double dot plus phi transpose times k times phi times z is equal to then phi transpose times r. Okay, let's call this equation 14. And what do we know? Well, we know that we've already said what this term must be, right? This must be the identity matrix. We also know what this term is, right? This is that spectral matrix, omega squared. And we're going to go ahead and define this quantity as r phi, just to remind you, this is a mapped force vector, right? So I can go ahead, this is equations 8 and 9, but I'm going to go ahead and substitute equations 8 and 9 into equation 14. And I'm going to end up with something that now looks very simple. Z double dot, which is a function of time, plus omega squared times z, which is a function of time, is equal to r phi, which is also a function of time, right? Let's call that equation 15. So what can we say now? Well, now it's going to become important that this omega squared matrix is diagonal, right? So we can observe that because omega squared is diagonal, the system of equations given in equation 15 are actually uncoupled. So what does that mean? That means that the governing equation for any mode I can be given as follows. Right? We could say that zi double dot plus omega I squared times zi is equal to pi, right? Obviously, zi and pi have a time dependence. Let's call that equation 16. And I'll just say where we can define pi is going to be equal to the quantity ui bar transpose times r of t. Okay? Call that equation 17. So that's a really simple equation for us to solve, right? So the only thing that we need to talk about now is how do we solve that? How do we get an initial condition? Okay, so the solution to equation 16 requires an initial condition for each zi. So how are we going to get this? We basically need to invert that equation. We had the mapping that u is equal to phi times z, right? We talked about that. So now we need to figure out how do we get z if we know u, because we're going to define our initial conditions on the basis of that, right? So let's go ahead to see that. Let's post-multiply equation 8 by phi inverse, okay? Okay, and what happens when we do that? Well, I had to begin with phi transpose times m times phi, and I post-multiply by phi inverse. And that was going to be equal to the identity matrix post-multiplied by phi inverse. Right, which means that that's just phi inverse. What's this quantity? Well, that quantity is the identity matrix, right? So the upshot to this is that I have that phi inverse is equal to phi transpose times m. And we'll call that equation 18. So now I can go ahead and invert equation 11 using equation 18. And then I end up with phi inverse times u, right, is equal to phi inverse times phi times z, right? That's the identity matrix. And I substitute 18 into here, and I end up with the following. I can say that z is equal to phi transpose times m times u. Okay? Let's call that equation 19. So if I have an initial condition that's defined on u, I can get the equivalent initial condition for z, just using this mapping, right? I can also, as you might expect, I need something for z dot in that equation, right? Because that could be another initial condition. So I'll just say also that similarly, we may write the following. Z dot is equal to phi transpose times m times u dot. Let's call that equation 20. Okay, so what can we say now? So basically, given initial conditions on u and u dot, we can find the corresponding initial conditions for z and z dot from equations 19 and 20. So now that we know how to solve all these equations, you might be thinking, well, that sounds well and good, but we still have an n by n system. We haven't done any reduction of the modes. We haven't changed that out. So how do we go about doing that? Well, it's a good observation. So let's just write that as equation 15 stands, it's going to yield an identical solution to equation 1, right? Because it's just a transformation of it. Okay? But we know that the benefit of modal analysis is that maybe only the lowest portion of the eigen spectrum needs to be retained. So how do we do that? Well, instead of using the mapping that we talked about in equation 11, which I'll remind you looked like u is equal to phi times z, right? Instead of using that mapping, we're going to approximate the displacement with some small number of modes. So instead of the equation 11, we'll have now instead that u, the displacement, is approximately equal to the sum over the modes that go from I equal 1 to m, where m is going to be less than n, and that will be then ui bar times zi, right? Let's call that equation 21. And I'll just note that where typically m is much less than n. So the question maybe comes into your mind, well, how do I know if it's good enough? How can I check the error? It's actually pretty straightforward. So the error can be measured using equation. If you use equation 21 to compute your displacement, you can measure the error in this following way. So we would say error, which is going to be a function of time, is going to be equal to the norm, however you want to define the norm, of r of t, right, that force vector, the reaction force vector, minus m, right, times u double dot, and u double dot is as computed above, right? Except, of course, if we were computing u double dot, we'd have a z double dot term there, right? Minus k times u, that norm, divided by the norm of r. And obviously this is just basically equation 1 saying r, the right-hand side minus the left-hand side. So if it's exact, this numerator will be 0. Okay, we'll call that equation 22. Let me give you a few concluding remarks about this method. Okay. Okay, remark number 1. Whatever reduced mode set that you choose, you're basically going to pick a maximum frequency that you care about. That reduced mode set must contain, without any omission, all the modes up to the chosen frequency. Okay, so what does that mean? That means that if I, let's say, pick 10 hertz to be my cutoff frequency, I say I think that my problem can be approximated by all the modes up to 10 hertz, but nothing above it. If I choose that, then I am obligated to choose all the modes from 10 hertz and below. I can't say, well, I don't really care about the 5 hertz mode. No, you can't do that. You have to have the entire set, okay? And then you might be thinking, well, how do I know what the cutoff frequency is? And you're going to not like my answer because the cutoff frequency is problem dependent. Okay, at the very least, the modes that you choose, the frequencies that you choose, must span the temporal variation of the loading. What does that mean? That means if I'm going to force a system, let's say at 10 hertz, right, I'm not free to choose frequencies from 5 hertz and below, right? I have to at least span the frequency that I'm applying the load at, right? Number 3, sort of a corollary to what I just said, the shorter the time of loading, right, you just have a quick bump or a quick impulse. If that loading is abrupt, so the more abrupt it is, the more modes are going to be required to capture it accurately. Number 4, as you might expect, hopefully from your intro class, you know that you need higher resolution if you need quantities that involve the derivative of the displacement, right? So if all you care about is the displacement, you may need a particular cutoff frequency. But if you want velocity, acceleration, right, those are derivatives of displacement in time, or maybe you need stress and strain or gradients, right, where you're going to now take spatial derivatives of that displacement, then you're going to need to increase the number of modes. And the final comment I want to make is that if the loading is spatially irregular, right, so it's not a uniform or homogeneous loading, but it has a lot of variability in it. If it's spatially irregular, you're going to also require more modes. Okay, so hopefully that gives you an overview of the modal analysis and kind of gives you also an appreciation for its power to reduce the computational burden of trying to solve for everything when you really only care about a small subset of the modes that are playing a role in your problem.